It's Mr. Pope from Winton Grammar School for Boys, and today I just wanted to go over in the ninth calculus section reduction formulae, curve length and surface areas of volume, or evolution, sorry, for integrals. Now I'm going to do this in a bit of a wacky order. I'm going to do curve length first and then use that to build on surface areas. And then reduction formula, there isn't really a general method per se. It's more of a technique you can use when dealing with integrals that you can kind of spot or reduce down into a pattern. So when I'm talking about curve length, imagine I've got a function. Let's say this is y equals f of x, and it's just behaving so and so like that. And let's say in a particular interval, let's say a to b, like that, I am interested in the length of this curve. Okay, I'm interested in the length of the curve on that interval. So the one thing I could do is I could say, well, I could break this down, and if I zoom in, I can imagine that I've got straight line segments where this is some change in y, dy, over some change dx. And that length line segment thing I will call delta, and clearly delta squared is dy squared plus dx squared. So really what I want to do is I want to sum up all of these things. I want to sum up all of the deltas in the limit that dy and dx tend to 0. Okay, now notice this is dy all squared, and then you've got something like this, and technically it's the square root of these things. So really, I want to take the sum of, using Pythagoras, the infinitesimal line segments and then sum them all up. Now the problem is we're not dealing with area this time, but to make integration make sense, we really need to have a dx on the outside. And what we're going to do actually is we're going to play around with this to force a dx to come on the outside. So notice that if I take a factor of dx squared out of this thing, I will have dy over dx all squared, but then I'll also have a plus 1 here. And now if I take that dx squared outside by square rooting it, I'll have the integral of the square root of 1 plus the derivative squared dx. And this is between b and a. And now I've got a nice little equation for my curve length on the interval. So if I want to know how long a curve is on a particular integral, all I need to do is take the derivative, square it, add 1 to it, square root it, and then integrate that between the two bits that I'm interested in. So say for example, I've got this. Let's take a really easy example. Let's suppose I've got a parabola and it's looking like this. So this parabola is y equals x squared, and I'm interested between 1 and 2 the length of the curve in that interval there. Well, we'll just do what the equation says, and let's separate this for good measure, make it nice and big and highlight it. So what does the formula tell us to do? Well, it says differentiate it, so dy by dx, which is 2x, square it to get 4x squared, and then to find that curve we'll call s, we'll call this curve length s. This is just the integral between 1 and 2 of the square root of 1 plus the derivative squared, which is 4x squared, and this is dx. Okay, well, that's going to be quite difficult to do. However, a couple of things we can do here actually. We can take a factor of 4 out, so this is 2 lots of the integral of 2, 1, and then this will be the integral. Well, in actual fact, we don't need to do that. We could just say this is 1 plus 2x all squared dx. And then we could say let u equal to 2x, so then we've got du equals 2 dx. So that means dx equals half du. So this is going to be integral, and on half du there, this is going to be the square root of 1 plus u squared. And then the limits, when x is 1, u is 2 lots of 1, which is 2. When x is 2, u is 2 lots of 2, that's a 4. So really, we've just got something like this going on. I wonder how we could do this. Well, now that we know a little bit about hyperbolics, we can spot maybe a substitution. For example, I know that cosh squared x minus sine squared x equals to 1. So cosh squared x equals to 1 plus sine squared x. So if I use the substitution, let u equals to sine of a, say, then du by dA becomes cosh of a dA. Now this is nice because this becomes a half of, and now if u is 4, then this is technically the inverse sine of 4. And this is going to be the inverse sine of 2. We'll leave it as that. And then the square root of 1 plus u squared, well, 1 plus u squared is 1 plus sine squared, which is cosh squared. So the square root of cosh squared is cosh of u. So this is actually cosh of a, sorry. And then du is cosh a dA, so this becomes cosh squared dA. And then to integrate cosh squared, this is another standard thing. Cosh of 2a, just like the trig thing, is 2 cosh squared of a minus 1. So if I add 1 to both sides, this is actually a half plus a half cosh of 2a. And this is cosh squared of a. So this actually becomes, I can take the half out, so this is a quarter of my limits, which I'll leave for now. And then it's 1 plus cosh of 2a dA. This can be evaluated as a quarter of 1 differentiates to just a, and cosh 2a, what will that integrate to? Well, cosh will integrate to sine, and the 2 needs to come out, so that's a half. And this is still integrated in the limits of the inverse sine of 4 and the inverse sine of 2. I've taken up a whole lot of space there. I should always give myself more pages, and I never do. So let's take this down. So the integral is actually 1/4 of a, and what did I say a was? Well, I said u equals to sine of a. Well, this is going to be interesting, isn't it? How about we just evaluate it as it is? So we've got a plus a half sine of 2a, which is going to be sine of a times by cosh of a. Because remember, sine 2a is just 2 sine a cosh a, but 2 times a half is just 1. And this is going to be integrated between the inverse sine of 4 and the inverse sine of 2. So notice how we were just dealing with just a really simple quadratic function. All of a sudden, just to find the length of it, we have to use hyperbolics. And it wouldn't seem intuitive why that would need to be the case, but by substitution it looks like that's going to be the case. So we're going to have a quarter of, and then from the a's perspective we're going to have inverse sine of 4 minus inverse sine of 2 plus, and then when I shine an inverse sine, that's going to be 4 cosh of an inverse sine of 4 minus, and then we're going to have a 2 lots of cosh of an inverse sine of a 2. Okay. Now, it'd be really useful to know what the inverse sine for an inverse sine of 2 was. So, I am going to look back at the formula sheet for this one. So, at Excel, formula sheet. I never actually remember. I know it's got. If I was to make a guess, I'd probably say it's ln of x plus the square root of x squared minus 1 is the inverse sine. I always get it the wrong way round, but you're always given it in the formula booklet, so I wouldn't worry about it. The very worst case, and your life depended on it, you could just complete the square and make it the subject by just rearranging the formula. It's not that big of a deal. Where is it? Nope. Inverse sine. Okay, it's a plus. Cosh is the minus 1. Okay, so inverse sine of 4 is ln of 4 plus the square root of 4 squared plus 1, which is 17. And then minus ln of, and then 2, that's going to be 2 plus root 5. So it's a quarter of this thing, plus 4 lots of cosine of the inverse sine, so it's going to be ln of 4 plus root 17, and then minus 2 cosh of ln of 2 plus root 5. To evaluate this further, remember that cosh of x is e to the x plus e to the minus x over 2. You're going to have to memorise that one. So when I've got ln of 4 plus root 17, remember when I take a minus log it becomes 1 over, so that's 4 plus root 17 plus 1 over 4 plus root 17, and then this is all over 2. So this is what it means when I do cosh of an inverse sine of 4. So I'm going to have all over 2 lots of 4 plus root 17, and then I've got 4 plus root 17 squared, which is going to be 16, plus 2 lots of 4 lots of root 17, which is 8 root 17, plus a root 17 squared, which is 17, and then plus the 1 from over here. What's that going to give? I've got 217, which is 34, plus 8 root 17, all over 2 lots of 4 plus root 17. The 2 and the 34 and the 8 cancel to give us 17 and 4. And then I can rationalise this denominator, and I'm going to times it by root 17 minus 4. The reason for that is because then it's positive. So root 17 squared is 17, minus 4 squared is 16, so this is going to be nice and just be all over 1. Then what I'm going to get, I'm going to have minus 4 lots of 17, so minus 4 lots of 17, and then I'm going to have plus 4 lots of 17 there, from the middle bit. And then I'm going to have root 17 times 17 there, so that's plus 17 root 17, and I have minus 4 lots of... No, and I'm going to have... Right, careful. This times this and this times this cancel. But I'm also going to get root 17 times this one, and this times this, which is minus 16. Oh wow, so the whole thing just becomes root 17. Because that and that cancel, this is one more than that, so it's just a single root 17. That's kind of cool. So cosh of, so this thing is just going to be root 17. And then let's deal with this. Ln of 2 plus root 3 when I cosh it. So that is going to become 2 plus root 3 plus 1 over 2 plus root 3 all over 2, because that's what cosh of ln of that thing becomes. So I'm going to have this thing squared, which is 4, plus, well, I'm going to have 4 lots of root 3, and then another root, so it's going to be a 7 plus 4 root 3 plus the 1 there, so it's actually 8 lots of this all over 2, lots of 2 plus root 3. And then the 2's cancel, so then that becomes a 2, that becomes a 4, this disappears. I'm going to times by 2 minus root 3, top and bottom. So that 2 squared is 4, minus root 3 squared is 3, so that's a 1. And then I'm going to have 2 lots of 2 root 3, and minus 4 lots of root 3, so they cancel. So the only thing that's going to be left is 2 times 4, which is 8, and 2 lots of root 3 times minus root 3, which is 2 times 6, that's minus 6, that's actually 2. Wow, so that's just a 2. So the answer at the end of the day is going to be 1/4 of ln of the first thing, which is 4 plus root 17, over 2 plus root 5, and then plus 4 root 17 minus 2 lots of 2, which is 4. Right, actually, can we do better than that? Is 4 plus root 17 over 2 plus root 5, that can be written as root 5 minus 2 over root 5 minus 2. The bottom is just 1, that's nice. And then I've got, let's do it first. So I've got 4 root 5 on the top. Wow, that's just not going to be nice because the root 17 and the root 5s are not cool. Anyway, so we'll just leave it as that. So, rather bizarrely, it's some number that's not particularly nice, but that is the exact length of that section of the curve between 1 and 2. And in general, it's not particularly difficult because usually the questions will be particularly constructed so you can do it quite nice and easy. It's just the example that I chose that I thought would be nice and easy actually turned out to be a horrible hyperbolic, but you just do it in the normal way. Okay, so what were to happen now? Now, by the way, what were to happen if instead of y being a function of x, how would you deal with it? And by the way, I don't think we need this stuff anymore, do we? Well, I'll tell you what, we'll shrink it down, we'll put it in there. If y is a function of x, then this is what you'd do. But suppose that now x is a function of y, and how would we go about doing this? And essentially it wouldn't be any different. The curve length, which I'll call L, would just be the integral between now y is b and y is a, and this is going to be the integral of 1 plus dx over dy all squared times by dy. So what does this mean? It means I've got like a curve doing something like that, and for some particular y value, let's call that b, and for some particular y value, let's call that a. I'm interested in the length of this green curvy bit here. Okay, so whatever I show you, whether it's in x or y, you can just kind of figure these things out for yourself. There's other things you can do as well. For example, how would you do it in polar coordinate form? So, okay, well, just remember what polar coordinates are. R is a function of theta, and x equals cosine theta, or r is x equals r cos theta, and y equals r of sine theta. So when I'm integrating stuff, when I'm doing 1 plus dy by dx, and that's all squared dx, we'll think about this very carefully. dy by dx is just going to be dy d theta, which is r cosine theta over r dx d thingy, which is minus r sine theta. Well, you can probably figure these things out for yourself. The long and short of it, and you'll be given these in the formula booklet, is that when r is a particular function of theta, this boils down to r squared plus dr by d theta all squared, and then this is d theta. In actual fact, should we just prove it and be done with it? So say I've got a curve, it's like that in polar coordinates, and I don't know, I'm interested in this section of the curve where I'm going from here to here and from here to here, and clearly this is theta 1 and it's up to theta 2, and arc length is clearly just r d theta. You can probably figure out the rest actually. You know, you can do similar Pythagorean things between two things like that. You know, it's much of a muchness. I could spend another 20 minutes going through it, but I'm kind of a lost end here. I've got two other things I want to get through today, but the point is, this is the equation for arc length. If you want to prove it yourself, then I've given you a starting block for sure. What was the other thing I wanted to talk about? Oh yeah, well, with the parametric case, so say I've got, and to be fair, polar coordinates is very similar to parametrics. Let's say I've got x is a function of time, or t, and y is a function of t, and let's not use purple because that's being used again. Mate, come on. Like so, let's pick pink. Then the curve length, which we'll call L, is going to be integral, and this time your t values are the things that are up here. And now this is just going to be the integral of dx over dt squared plus dy over dt squared dt. And if you want to, you can probably actually see that dt is actually just dt all squared, and when you times these two things together, you get the integral of dx squared plus dy squared and so on. And in actual fact, you can probably see that's what's happening over here. I mean, look, let's convince ourselves it's the case. Then we're going to have the integral of the square root of r squared plus dr over d theta squared squared, and this is times by d theta squared, because that's what, I mean, d theta is just d theta squared square rooted. If we bump that in, then what's going to happen? Then when we redistribute all these terms, we're going to get something looking like this. So so we're going to get r squared d theta squared plus dr squared. I wonder how that corresponds to the diagram. Well, if I've got a particular arc, you know, and well, what do I want to know? Well, r d theta is going to be the arc length. Dr squared is the change in r. Ah, maybe that's what it is. Maybe you're treating it as something like that, where you're not really, but you're assuming that it's becoming a right angled triangle like this, where if I've got a radius going like that and a radius going like that, then the difference between these two radii is this thing. This is dr, and then this height here is clearly, well, it's supposed to approximate, when theta is really small, r d theta. And so by Pythagoras, the length of that, which would be the hypotenuse, would just be this. So yeah, that's one way of convincing yourself that's the case. Okay, so we've got a lot of things here. So this is for the parametric. This is for the polar. And in actual fact, this is taking up way too much space. Oh wow. So let's shrink this up here. And let's this has served its purpose. Let's put it there. And let's put that there. So this was just an example, and then for the polar case we had this, and for the parametric case we had this as well. So this was consider blah, 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 blah. And this we're going to make big. So for the polar case we've got this. For the parametric case, we've got this, and yeah, and for the normal Cartesian stuff, we've got that. Okay, now there's various things here, because now we're going to be looking at surface areas. Okay, so let's copy. Okay, surface areas. Now we're going to define these much in the same way that we did volumes of revolutions before. That is, if I've got a surface, here it is, and suppose I rotate it about the x-axis. So between here and here, I rotate it about the x-axis. It's going to do something like that, and it's going to create a solid, you know, looking like that, some rotational shape. Then what I'm interested in is I'm interested in the surface area of this shape, i.e. just, you know, the kind of like the lampshade part, if you like. This would form a lampshade. I just want the surface area. So what would happen here? Well, what I would do is I would just use the fact that, well, the surface area, I would just split this up into circles, or I'd break them up into cylinders that have surface area. Normally, they're 2 pi r times by r plus h, right? Because it's 2 pi r squared plus 2 pi r h. Now the surface area of the cylinder, I don't really care about the circular bits at either end. So the 2 pi r squared bit's not the interesting bit. It's actually the 2 pi r h bit. It's the 2 pi r h bit that's being rotated around. Now what is r in this case? Well, r is just my f of x. It's my function. It's my y. So it will be 2 pi, whoops, it will be 2 pi of y. And then what is my h? My h will just be my infinitesimal slither dx. Or is it? It's actually not. In this case, we want the height to be the length, okay, of the curve at that point. And that is clearly going to be the integral of dy squared plus dx squared, and then sum all of this. Right? The reason why it's just not dx is because that would find the surface area of any shape within the interval between here and here. So it wouldn't matter if the shape was doing something like this, or there was a straight line, or had a slight curve, they'd all have the same surface area. What it depends on is not the interval dx, but actually the length of the curve. So, and we've seen this stuff already, this can just be written as 2 pi, the limits between a and b of y, lots of the square root of 1 plus dy over dx, all squared dx. And now, this I'm going to call S for surface. So we now have a formula for the surface area of a shape that's been rotated around the x-axis. So this is rotated about the x-axis. Now if I wanted to rotate it about the y-axis, that's quite easy to do. That's just going to be 2 pi of this time between y is b and y is a, and this time it's x, lots of the integral of 1 plus dx by dy, all squared dy. All I've done is substituted x for y, and now this is going to designate to a rotation about the y-axis by symmetry. So this is rotated about the y-axis. Well, what about parametric? Well, if you know, it's the same as before. The parametric stuff is going to be very similar. Just this time it's going to be s equals 2 pi of, now t is between some values, not necessarily the same, so let's call them a1 and b1. And this time it's going to be y and the square root of, and this is going to be dy by dt squared plus dx by dt all squared dt. And if I wanted it, and this is rotated about x, if I wanted it rotated about y, I'd switch the x and y's around. It's not that big of a deal. This would become an x, and essentially the bit in the middle would become the same, so it's not really that big of a deal. For polar coordinates, bit of a pickle, but honestly not that deep. And you can prove this yourself should you wish to. But if you want to rotate it about the initial line, or the x-axis if you like, then this s will be 2 pi, and now it will be between the two angles, theta equals a and theta equals b, and let's call this b1, let's call them a2 and b2. Then it will be r sine of theta, and then the same line integral, r squared plus dr by d theta squared d theta. Okay. And now, if you don't want to rotate it about the initial line, say you want to rotate it about the y-axis, which is also some line, let's say theta equals to plus or minus pi over 2, right? Because the x and y-axis isn't really a thing in polar coordinates. Then it's the same deal, 2 pi, and this time your thetas are still between b2 and a2, but this time instead of r sine theta, it's r cosine theta. And this is r squared plus dr over d theta squared d theta. And there you go. So before we begin, are those formula given to you in the formula sheet? Let me just have a double check. Arc length is, oh wow, they're all given in the formula sheet. That's fine. That's the point. Okay, so let me asterisk in orange which ones are given in the formula sheet. So the arc length ones, you're given this one in the formula sheet. You're not given the y form. You're given the polar and the parametric one. And then for the surface area, you're given the Cartesian one for x, the parametric one for x, and the polar coordinate one for x. So really, if you know all the ones for x rotated about the x-axis, and they've all been subscripted s of little x, for example, just to remind you it's rotated around x, it's honestly not going to be that big of a deal, honestly, because you can just swap the x's and y's around and you know how to rotate it for y's. So really, all of these formulas I've given to you, you can derive them by thinking about the shape and just applying calculus to it. And the other thing is they're given to you in the formula, so you don't really need to know them. But I've been saving the best for last, in my opinion. And that is reduction formulae. Okay, now reduction formulae are incredibly powerful. I was thinking about it last time because I think the last time I did a calculus video, I did volumes of revolution, and I think what it boiled down to is I was stuck, and I had to integrate cosec of theta cot to the power of 4 theta d theta, and I had to find out what that was. I'm just trying to think what the bounds were. I want to say it's between 2 and root 2. Yeah, something like that. Actually, let's have a quick Google of this. Well, let's go back in here. Where was it? Volumes of revolutions. No. Yeah, volumes of revolutions. Da, 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 da. It's the last question, wasn't it? It was pi over. Oh no, it was the. Yeah, it was that between 2. Oh, okay, so it's pi over 3 and pi over 4. Okay. So I actually want this to be between pi over 3 and pi over 4. Okay, so I was actually thinking about it the other day. This integral caused me a bit of a beef. Is there a sexier way I could have done this? And in actual fact, it turns out there could have been. I didn't think of it at the time because I wasn't thinking of reduction formula, but actually you can solve this quite nicely for reduction formula. Now, what reduction formula is really good at is spotting a pattern and building up integrals as like parts. So to solve this integral, let's suppose we'll define integral I of n such that this is the integral between pi over 3 and pi over 4 of cosec theta times by cot to the power n of theta d theta. Right, and essentially this thing up here is just now I of 4. And what we're going to do is we're going to solve for the general case of I of n, and then realise that that essentially makes building blocks. So we can actually work up to I of 4. Because I of 0 is actually incredibly easy to deal with, because it's just pi thirds pi 4, and then it's just cosec of theta, and then cot to the 0 is just 1, so all we have to do is just integrate cosec theta d theta. Now if I look at the formula booklet, because I always forget what cosec, it's like ln cot sec, isn't it? I can't remember. Something like that. Where is it? Cosec. No, they're the hyperbolics. Oh no. Cosec differentiates to that, but cosec, right, okay. So this actually becomes the negative log ln of the mod of cosec x plus cot of x. And this will be evaluated between pi over 3 and pi over 4. And just to make this whole thing quicker, I'm going to remind myself that cosec of x, cosec of pi over 4 is 2 over root 2, or just root 2. And cosec of pi over 3. Should have done that first, really. Cosec of 60. Well, sine of 60 is root 3 over 2, so that's 2 over root 3. And then cot of pi over 3. Well, tan of 60 is root 3, so this is actually 1 over root 3. And then cot of pi over 4 is just 1. So actually, this integral is quite easy. It's minus the log of, and then when I sub pi over 3 in there, it's going to be when I add those two things together, which is 3 over ln 3, which is just ln 3, minus the minus log of, and then when I sub pi over 4 in there, that's going to be root 2 plus 1. So I've clearly got a plus log there, so it's actually going to be ln of root 2 plus 1 all over root 3. So this is what I0 is, and generally speaking, if I can write I4 as something of I1 and I2 and I3 and something like that, then we're generally going to be into a good time here. So it's not a problem. Okay, so we just need to get on with it really. What happens if we integrate I of n? So here's hopefully a nicer way. I of n is the following. Well, I don't know how to integrate cot to the power n, but I do know how to differentiate it. The other thing is that I know how to integrate cosec cot, that's just cosec. So what I'm going to do, actually, I'm going to give myself some space. It seems a bit silly to do this again, but you know, just to prove a point, this can be written as the integral of pi over 3, pi over 4, and then I'll write this out as cosec theta times by cot of theta, and then times by cot of n minus 1 theta d theta. So all I've done is taken a factor of cot out and moved it over to there. Because now if I do integration by parts and set this as my v dashed, and I set this as my u, I can now integrate fairly nicely. So if u is the cotangent of n minus 1 theta, then u dashed is going to be the differentiation of that, which is going to be minus n minus 1, bring the power down, and then cosec squared of theta times by cot of n minus 2 theta. Bit of a mouthful, but it can be done. And then v dashed is cosec theta cot theta. And the reason I picked that is because when I integrate that, that's quite nice. That just becomes minus cosec of theta, like so. Okay, so that means I of n will become u times v. So I've actually got minus cosec theta times cot of n minus 1 theta. And this needs to be evaluated between pi over 3 and pi over 4, minus the integral between pi over 3 and pi over 4 of v du. Well, the minus times this minus will cancel, so that's gone, but there's still a minus on the outside. I've got an n minus 1 on the outside, so that's n minus 1. And then if I think about it, I've got a cosec theta times by a cosec squared, so that's a cosec cubed theta, and then this is times by cot to the n minus 2 theta d theta. And you're probably thinking, oh dear, you've just made it worse. Why did you do that? Well, and I'll remind you again that 1 plus cot squared theta equals to cosec squared theta from your trig things. So I can break this cosec cubed into cosec theta times by 1 plus cot squared theta times by cot to the n minus 2 theta. So this actually is cosec times 1 times this, which is cosec theta times by cot of n minus 2 theta, plus, and then cot squared times cot to the n minus 2, that's just going to become cosec theta times cot to the n theta d theta. Why is this nice? Because now This thing is just my integral I of n subscript of I subscript n minus 2, and this thing is just I of n. That's so nice, because now we've got I of n equals this thing here, which is minus cosec theta cot of n minus 1 theta, evaluated between pi over 3 and pi over 4, minus n minus 1 lots of, and now it's just n of I of subscript n minus 2 plus subscript I of n. Notice how it's exactly in this form. I just have now changed this n and this n to n minus 2 over here. So that's clearly I of n minus 2. Okay, if I get all the I of n's to one side, then on the right hand side I've got minus n minus 1 lots of I of n minus 2's. If I add an n minus 1, then I believe I've actually got n lots of in on that side, and this is going to be the same thing over here. So I'll just copy this and put it down. And then all I have to do now is divide by n. So 1 over n is there, and 1 over n is here. Now, this reduction formula tells me exactly what I need to do. Because now, suppose I want to work out I4, then that means I need to do 1 over 4 of the evaluation thing of this thing, between pi over 4, minus 4 minus 1, which is 3, over 4 lots of I of 2. And I know how to work out I of 2 because I can just go one step back. I of 2 is 1 over n, where n is 2, lots of, evaluate this thing between pi over 3 and pi over 4, minus 2 minus 1, which is 1, over n, which is 2, I naught. Ah, I know what I naught is now, so I can just plug it all back in. This isn't actually that much of a deep thing. And when you do all that, you can actually get the answer. I'll leave it to you, but essentially what I've done there is I've broken down it into 2 steps. And to be honest, this question would have been just as laborious. It would have been, I would have broken the question the same way if the original question was, say, cosec theta cot to the 24th power theta. Then in that case, I would have just kept going in 2. So I'd have worked out I0, then I2, then I4, then I6, and then so on and so on, I20th, I22nd, and then I'd have gotten to I24th. You know, it's much of a muchness. It seems laborious, but it means that really difficult integrals that have really weird powers or some kind of relationship can now just be broken down into something that a computer can just do given the time. And to be fair, you could do it, you just can't be bothered to do it. Now I'm going to go through some examples of this reduction formulae stuff, but essentially this is what all I wanted to go through today. I mean, this stuff, if I was to put an asterisk for it, I'd give it an asterisk and a half, because it's not in further maths. It used to be in the further pure 3 module. It's in the further pure 2 module now, so there's a very high likely that if you were doing further maths now, you'd never see this. However, the reduction, I mean, the curve length and the surface area, you just kind of know from like the first semester of a mathematics degree. But the reduction formula I just find is incredibly useful. It will help with step questions. It's just useful to break down more complicated integrals. So, how are we doing for time? 49 minutes, cool. I've got, because there's 3 things I wanted to go through today, I've got quite a few questions. So, yeah, if you want to give this a go, pause the video, and yeah, I'll see you in a second. Okay, first part, find an expression for that. Okay, well, first thing, I'm going to go to my formula booklet, and I'm going to see if I've got any integrals for 1 over square roots of things, because I get the funny feeling that's going to be a hyperbolic thing. Yeah. Okay, so it's not, but put it this way, the integral of 1 over the square root of 1 minus x squared dx, that is just arc sine of x. So I spot something like that's going on here. I'll tell you what, we'll just run with it. So the first thing I'm probably going to do is take a factor of 25 out of the bottom. So that is going to be 1 over 5 on the bottom, and then I have x on the top, and then this will be the square root of 1 minus x over 5 all squared dx. And now let's say let u equal to x over 5, so that 5 du equals to dx. Yeah, that's possible. Then what's going to happen is this 5 and this fifth cancel. I've got a 5u on the top, so actually that 5 can go on the outside. And then on the bottom, I've got a 1 minus u squared du going on here. Okay, how about I let u equal to let's let u equal to sine of let's pick a different thing, theta. Then du is going to become cosine theta d theta. Then what are we going to have over here? We're going to have 5 lots of u on the top, which is sine of theta, over 1 minus sine squared is cos squared, square root that is cosine theta, and du can be replaced with cos theta d theta. The cosine and that disappears, integrate sine becomes minus cosine, so this actually becomes minus 5 cosine theta plus a constant. If sine theta equals to u, then what have we got here? Then u squared equals to sine squared theta, and 1 minus u squared equals 1 minus sine squared, which is going to give a cosine squared theta. So if I square root that, I'll actually get minus 5 lots of the square root of 1 minus u squared plus c. Technically I square rooted it, so it could be the plus or minus square root. I'm going to take the principal branch of the positive one for now, and I'm going to check to see what happens here. And then finally u was x over 5, so this becomes minus 5 of the integral of 1 minus x over 5 all squared plus c. So this is actually going to be 25 minus x squared all over 25 square rooted minus 5. So actually this and this are going to cancel. So I make it that it's the negative square root of 25 minus x squared plus c. And just to make sure everything is okay, I'm going to now differentiate this thing and see if I get back to my integral. So this is actually minus 25 minus x squared to the power of a half. So the first thing I do is I bring the half down, so the half is here, there's still a minus, times by. Differentiate the thing in here, so that's going to be times by minus 2x. And then I've got 25 minus x squared, and then I reduce the power by the chain rule. The half and the 2 cancel, the minus and minus cancel, so I've actually got x times by this to the minus half, which is x over the square root of 25 minus x squared. And that is what I wanted because, yes, so in actual fact, I was right in taking the negative branch over here. If it turned out that when I did all this stuff, I'd have minus that, then I'd have taken the negative, the positive, sorry, and so on. So it looks like negative root of, yeah, it's right. You can just do a differentiation check to see if you picked the right one, is what I'm trying to say. Right. B, using to answer to part A, show otherwise that I of n equals that. Okay, so look, very carefully, what have you actually done? Well, what you've actually done, you've actually worked out what I of 1 is, haven't you? Um, okay, fine. How about we write it down? We just write it down. We play. Being able to do these things is quite difficult. Not because the process is difficult, but spotting what you need to do is actually quite tricky. So between 5 of 0 of, let's say, x to the n over, what is it, the square root of 25 minus x squared dx. Okay, well, I know how to integrate x over that. So maybe I'm going to do some by parts stuff and say this is actually between 0 and 5 of, let's say, x to the n minus 1 times by, and then this is, say, x over the square root of 25 minus x squared dx. I have no idea if this will work or not. I don't know. So let's suppose this is my v dashed, and I know how to integrate that, and let's say this is my u. Then by parts, u is x to the n minus 1, and u dashed is going to be n minus 1, lots of x to the n minus 2. V dashed is, well, what we've got, which is x over the square root of 25 minus x squared, and v is just going to be the negative square root of 25 minus x squared. That's it. So what have we actually got? We're going to have u times v, which is going to, so in is going to be the negative x to the n minus 1 times by the square root of 25 minus x squared, and this needs to be evaluated between 5 and 0, minus the integral of v du. Well, that minus there is going to cancel out with this. I've got an n minus 1 coming out at the front as a factor, and then I'm going to have x to the n minus 2 times by the square root of 25 minus x squared dx. Okay, not nice at all. But there's some things we can do, right? And when you look at it, actually, this is kind of cool, because if I look at the first thing, when I let x equals to 5, then the square root is 0. So 25 minus 5 squared, that turns to a 0. And then when I let x equals to 0, x to any power, when x is 0 as well. So actually, this whole first part becomes a fat 0. So what we're actually left with is I of n equals to n minus 1 of the integral between 5 and 0 of x to the n minus 2 times by the square root of 25 minus x squared dx. Now, this is the really tricky bit. To spot this takes a lot of skill, actually. What I'm going to do is I'm going to get this. Now notice, for in to work, I have to have a root 25 minus x squared on the bottom. So if I make this as a fraction over root 25 minus x squared, that means I've got to times it by that much on the top as well. Okay? Do you see why that's the case? Because if I've got this to the 1, and I've got this to the half on the bottom, then by indices laws, 1 minus a half still gets all to the power half on the top as well. Now, this is really good, because now I of n is going to be n minus 1 of the integral between 5 and 0 of, and then I can redistribute the top. I've got x n minus 2 times that, so I've actually got 25, lots of x to the n minus 2, all over 25 minus x squared square rooted, minus, and then x to the n minus 2 times x squared is just x to the n over 25 minus x squared square rooted dx. And now I can just put a dx there, integral there, 5 and 0, and I've split up the two integrals into their bits. Remember, they're both being multiplied by n minus 1. Okay, next up, I spot that if I can take 25 out as a factor, I can move this integral over a little bit, like so. So there's a 25 there. Notice how this thing is now I of n minus 2, and this thing is now I of n. So we've actually got I of n equals 25 lots of n minus 1 lots of I of n minus 2 minus n minus 1 lots of I of n. I believe so. Now all I have to do is add this over. So I believe I'm going to have n lots of I of n equals 25 lots of n minus 1 lots of I of n minus 2. And then when I divide by n, I'm just going to have that. So was I of n supposed to be 25 n minus 1 all over n of I of n minus 2? Yes, it was. So that's a fairly nice result, actually. And this one is a lot easier to deal with for the next stage and so on than my previous example of this trigonometric thing, because I had to keep evaluating this horrible thing here. But at least this is a lot easier now. So now for part C, find I of 4 in the terms of k pi. Well, I of 4 is just going to be 25 lots of 4 minus 1, which is 3. So 3 times 25 is 75 quarters, lots of I2. And I2 is going to be, well, that's when it is 2, so I've just got actually 25 halves of I0. Well, so if I whack these together, I4 is 75 quarters of I2, which is 25 halves of I0. So what have I got here? I've got 3 times by 5 squared times another 5 squared, so this is 5 to the 4, all over 2 squared times 2, so that's 2 cubed, and this is times by I0. So actually, this becomes really good because all I have to do now is integrate I0 and times it by this horrible thing here. So if I whack that down there, all I have to do now is find I0, and that is just going to be the integral between 5 and 0 of 1 over the square root of 25 minus x squared dx. I believe that's what it was. Yes, so when n is 0, that's just 0, that's just 1. So, same deal. I'm going to take the fifth out, so this is between 5 and 0 of 1 over the square root of 1 minus x over 5 squared dx. I'm going to pull the same tricks as I did before, but this time, well, what would happen? I just wouldn't have this u on the top, would I? Well, I'd let u equals x over 5 and so on and so on and so on. So if you let u equals to x over 5, then this is going to be the integral between 1 and 0 of 1/5 of 1 over the square root of 1 minus u squared, and du equals 1/5 of dx, or rather 5 du equals to dx, so that disappears, that becomes this, and now I know straight away this integrates to arc sine of u between 1 and 0, and arc sine of 1 is pi over 2, minus arc sine of 0 is 0, so that answer is pi over 2. So now all I need to do is say that I4 is 3 times 5 to the 4 over 2 cubed times by pi over 2. Well, I am definitely using a calculator for that one. So what fraction of pi is that? It's not going to cancel down because they're all primed up. So 3 times 5 to the 4 over 2 to the 4, we're looking at 1,875 over 16 lots of pi. Coolsies. So that's what that was. We didn't actually have to work out what x to the power 4 over that thing was, which would have been absolutely horrendous. Where k is a fraction, there it is, 1,875 over 16. Okay, have a look at this question, pause the video if you want, let me know how it goes. Okay, a curve which is part of an ellipse has parametric equations blah, and the curve is rotated through 2 pi radians about the x-axis. Show the area of the surface generated is given by that integral, where k and alpha are constants to be found. Right, okay, so what's going on here? X is 3 cos theta. Well, I mean, when theta is 0, cosine of 0 is 1, so x is 3. And when theta is pi over 2, x is 0. When y equals 5 sine theta, when theta is 0, sine theta is 0. And when theta is pi over 2, sine is 1. So we're actually dealing with this kind of egg-shaped... mate, what's going on? There's 5, there's 3. It's this weird, that part of an ellipse. The curve is rotated through 2 pi radians about the x-axis. So we're going to create this kind of eggy dome thing. Like so. It's not a problem. So we've got formulas for this kind of thing. So if I go to my parametric form of a surface area, there it is. So let's copy and paste this doodah. Okay. So rotating 2 pi radians about the x-axis is going to happen to be something like this. Fine. So let's get rid of all this other stuff. So what do we need to know? We know what y is. Y is just 5 sine theta. Do we know what d... by the way, these aren't t's, are they? These are going to be thetas. So really, the formula should be dy d theta, dx d theta, and this is a d theta out here. And these limits are in terms of theta. Okay, part of me thinks the limit should be between 0 and pi over 2, but it might not be that case. We'll have to have a look. Okay, so, let's have a look. Do we know what dy by d theta is going to be? I think so. That's just going to be 5 cosine theta, and dx d theta is going to be negative 3 sine theta, because cosine differentiates to minus sine. Okay, so for now I've got 2 pi integral between 0 and pi over 2 to trace out the whole shape, and then y, which is 5 sine theta times by the square root of dy d theta squared, which is 25 sine squared theta, plus dx d theta, which is 9. This is cosine, isn't it? Is this cosine? Yep, cosine, because y is already sine. Yep, so this is 9 sine squared theta d theta. Okay, so I'm pretty sure I've got this to begin with. First of all, I can deal with this a little bit because I'm going to have, well, 25 cos squared can be written up as 16 cosine squared theta plus a 9 cos squared theta, and then I've already got a 9 squared sine theta there, so that can cancel down to just 9, because cos squared plus sine squared equals to 1. So this is going to be 2 pi theta, pi over 2, 0, 5 sine theta times by the square root of 16 cosine squared theta plus 9 d theta. So, stuff's happening now. Because I'm almost there. I mean, I've got this bit right, but somehow the 5 sine theta shouldn't be there. That's interesting. Why is that the case? No, I've done that bit right. Does that 5 sine theta cancel down anywhere? Oh, wow. No. think they want me to do a substitution. Okay, so if C does equal cosine theta, I thought that was just shorthand. Okay, interesting. Then dc by d theta, well, cosine differentiates to minus sine theta, doesn't it? So that means, oh yeah, I should have noticed because this has got a dc at the end. Yeah, it's definitely a substitution. So you've got that. Oh, jeez. Okay, so let's deal with this a little bit. Oh man. Right, I need. Oh, that's really hurt my chest. Oh, let's do it down here. Oh man, that's. Ow. Right, so C equals cosine theta. Then dc equals to negative sine theta d theta. So what have we got here? I've got a sine theta d theta. I can get rid of that minus and put the minus there. So actually I can replace these two things with a minus 2 pi integral of 5 square root of 16c squared plus 9 dc. And then when theta is pi over 2, cosine of pi over 2 is 0. And when theta is 0, cosine of 0 is 1. So then I can take rid of the minus sign out and I can have a 10 pi, the integral between 1 and 0 of the square root of 16c squared plus 9 dc. I think that's right, isn't it? Is that what we wanted? So some amount of pi, integral between 0 and something of the square root of 16c squared plus 9 dc. Yes, so actually k equals 10 and alpha equals to 1. Okay, so that's part A done. Part B. Using the substitution, C equals 3/4 of sine u, or otherwise, evaluate this integral and give your final answer to 3 significant figures. Well, that's not nice. Cool. Right, so if C equals 3/4 of sine u, then dc is going to equal 3/4 of cos u du. Right, so we're going to have 10 pi of the integral of, well, when c is 1, that means sine u equals to 4/3. So this is going to be the inverse sine of 4/3. And when c is 0, then u is 0, because inverse sine of 0 is 0. Well, what is c squared? That's going to be 9 over 16 of sine squared u. If I times that by 16, that's 9 sine squared u. If I add 9 to that, so it's now up here, this is actually 9 lots of sine squared u plus 1. And sine squared u plus 1 is actually cos squared. So the square root of this thing actually becomes the square root. Just becomes 3 lots of cos u. Wow, that's nice. And this is still dc. Oh, wait a minute. Yeah, and dc can be replaced with 3/4 cos u. So actually, this becomes 9/4 of cos squared u du. Okay. Okay, so then I can take the 9/4 out, the 4 and the 10, that becomes a 5 and a 2. So that actually becomes 45 pi over 2 integral between inverse sine of 4/3 and 0 of cos squared u du. And again, whenever you're integrating sine, cos, sine or cosine, you want to consider cosine of the double angle, or sine of double angle, cos or cosh of the double angle, because this is 2 cosh squared u minus 1. So actually cosh squared u is going to equal a half plus a half cosh 2u when you rearrange it. So actually this integral becomes 45 over 4 pi integral of the stuff and the stuff of 1 plus cosh of 2u du. And when I integrate that, it's going to be u plus, and cosh 2u becomes a half of sine 2u. Oh, it's like before, isn't it? Wow, this is pretty much just like, you know, it's got our u cosh u's business that we had over here. That's really bizarre. It's very weird that would happen. Oh no, skipped it. Right, okay. Yeah, and this is going to be 45 pi over 4, and this is going to be between inverse sine of 4/3 and 0. So really, when I sub 0 into all these things, that's 0. So actually what we've got is 45 over 4 plus, no we haven't, we've got 45 over 4 lots of inverse sine of 4/3 plus a half of sine of 2 lots of the inverse sine of 4/3. They wanted it 3 significant figures, so I have no reason to I just have no reason to put it. Alright, now I need to find my hyperbolics. My calculator, where's my hyperbolics? On your normal Casio FX 83 and 85, you should have a HYP button. On the Casio FX 9918, I know where that is as well. But, there it is, hyperbolics. So we've got 45 over 4, lots of inverse sine of 4/3 plus 1/2 of sine of 2 lots of the inverse sine of 4/3. Close that bracket, close that bracket, close the big bracket. And apparently that's 37.359388825. So to 3 significant figures, I make that 37.4. Was it to 3SF? Something like that. Have I made a mistake somewhere? Yeah, maybe. I feel like this should have been a lot nicer. No. Where have we gone wrong? What am I trying to do? Right. Legit, I would have gotten 9/4 of 10 pi of the 2 bounds. Yep. And then that would have become... Okay, so I've got 90 over 4. And then I would have halved it again to get that. Don't cost 2u, yeah. Yeah, no, that's legit. Was it the substitution at the end that I've messed up? I don't trust my calculator, that's the problem. Oh, is it because it's in degrees? God damn. Let's get it in radians. Shouldn't make a difference, but okay. So I'm saying, oh my god, I forgot the pi. Such a wally. Oh my god, 45 shift pi over 4. The radians wouldn't matter. Inverse sine of 4/3, close brackets, plus fraction of sine of 2 lots of inverse sine of 4/3, close brackets because of the inverse sine, close brackets because of the sine, close brackets for the whole thing. Oh my god, such a wally. I forgot the pi. Wow. So that's 117.3679797 and so on. So to 3SF, that's 117. Wow. Can't believe I forgot the pi. Such a wally. Okay. Next question, if you want to give it a go. Pause the video. Okay, so for some integral I of n, we've got that it's the integral between 0 and a of a minus x all to the n cosine of x. Show that for n is greater than or equal to 2, you've got the following. Okay, well, how about we just go and do it? So we've got I of n between 0 and a of a minus x to the n cosine of x dx. I'm probably going to let this thing be my v dashed because I can integrate cosine to sine and let this be my u. So if u equals a minus x to the n, then u dashed appears to be minus n lots of a minus x to the n minus 1. If v dashed equals cosine of x, then v is just going to be sine of x. So this integral is just going to be u times v, which is a minus x to the n times by sine of x, and this is evaluated between 0 and a. And in closer inspection, this is just going to be a big fat 0, because if I sub a in, then a minus a is 0, and if I sub 0 in, then sine of 0 is 0, and it's perfectly fine. Minus the integral of v du. Well, that minus there is going to make this a plus, and I can take the n out, and then this is going to be a minus x to the n minus 1 lots of sine of x dx. So in actual fact, I've now got I of n equals just the integral between 0 and a, and I should have put that over there, of a minus x to the n minus 1 lots of sine of x dx. Okay, I think I'm going to have to do integration by parts again, choosing very similar things, i.e. let this be my v dashed and let this be my u. And I think this is going to give something useful. So if u is a minus x to the n minus 1, then u dashed is going to be 1 minus n, because it's essentially n minus 1 times a minus, and this will be a minus x to the power of n minus 2. V dashed is sine of x, and sine of x comes from when you differentiate minus cosine of x, I believe. So we've now got u times v integrated between 0 and a, but that's not going to be interesting. So it's going to be a minus x to the n minus 1 times by minus cosine of x between 0 and a. That's interesting, because when I substitute a in, then this is 0, but when I substitute 0 in, this becomes a 1, and this becomes a minus 0. So the whole thing actually becomes a to the power of n minus 1. I wonder if there's any a's to the n minus 1s. Yeah, there is, boy. Okay, cool. Minus the integral of v du. Well, I've got a minus there, so that's going to make that minus. This is going to be a 1 minus n, and then I've got a minus x to the power of n minus 2 times by cosine x dx, evaluate that's between 0 and a. And if I squint my eyes really carefully, this whole integral here is I of n. So what we've actually got is I of n equals a to the n minus 1 plus 1 minus n lots of I of n. Ah, that's I of n minus 2, sorry. Cool. I don't think that's what was happening, was it? Yeah, I've made a boo-boo here. Oh, that's what I've done. It's n lots of this thing, isn't it? So it's n lots of this thing, so it's n lots of everything, so it's n lots of that and n lots of that. So it's going to have an n there and an n there. And then I just take a factor of minus 1 out of there to make this a minus n lots of n minus 1, lots of I of n minus 2. This is n lots of a to the n minus 1. This equals I of n. Yeah, so I'm just sloppy. That's bad. That's poor of me, in all fairness. But yeah, it does actually indeed equal that result, so that's not a problem. Hence evaluate this. Okay, so from closer inspection, this is clearly when a equals to pi over 2, and we clearly want to work out I of 2. So according to this formula, we're going to need I of 0. So what is I of 0? Well, I of 0 is when this whole thing becomes a 1. So we just have to integrate between pi over 2 and 0 of cosine of x dx, which is just going to be sine of x between pi over 2 and 0. And sine of pi over 2 is 1, sine of 0 is 1, so that whole integral becomes a 1. So that means I of 0 is 1, and we want I of 2 when a equals to pi over 2, so we're going to have n, which is 2, lots of pi over 2 to the 2 minus 1, which is just itself, minus 2 lots of 2 minus 1, which is 1, times by in of that, which is just 1. So actually, I of 2 is going to be 2 lots of pi over 2, which is just pi, minus 2 lots of 1 lots of 2, which is just that. So actually, that integral is just this. So the integral of pi over 2, 0, of pi over 2 minus x all squared times by cosine of x dx is just pi minus 2. So actually that wasn't that bad of a question. Last two questions. Okay. So hopefully this is a nicer, easier question. So pause the video. Give it a go yourself. Okay. The curve C has equation y equals 2x cubed. The curve C is rotated through 2 pi radians around the x-axis. Using calculus, find the area of the surface generated. Okay, so the surface, I seem to remember, is going to be 2 pi between, it's defined between 0 and 2, and it's going to be, the square is going to be y, lots of 1 plus dy by dx all squared dx. Okay, so I've actually got 2 pi integral 2 0 y, which is 2x cubed, times the square root of 1 plus. Now the derivative of this thing is 6x squared. So I'm going to square that, I'm going to get 36x to the 4 dx. Mercy, mercy me. Right, so how am I going to do this? Oh, Jesus. Well, I wonder if a substitution might be in order, because I know that this thing differentiates to this. So if I let 1 plus 36x to the 4 equal to, say, u, then du is going to equal to 4 times 36, what's that, 144x cubed, and this is dx. Wow. Okay. So that means 2x cubed dx is going to equal 1 over 72 du. I make that. Yeah, if I divide by 72 both sides. So I know I can replace the 2x cubed and the dx with a 1 over 72 du. So that's going to be integral of 2 over 72, so that's going to be pi over 36. When x is 0, u is 1, and when x is 2, 2 to the power 4 is 4 squared, 16 times by 36, add the 1, wow, 577. And then this is going to be the square root of, lol, just u, du. So yeah, the numbers are nastier, but the actual integral is a lot easier now, isn't it? And then this is just, square root of u is just u to the half. Integrate that, it's going to be to the 3 halves, and then I've got 2/3 of 1 over 36, which boils down nicely to 1 over 54 times pi, and that needs to be evaluated between 1 and 577. Really? 577 is not going to be a square number, is it? So 577 to the power of 3 over 2. Yeah, that's not going to work. Oh man, really? Give your answer to 3 sig figs. Okay, fine, I can do that. So the answer to 3 significant figures is going to be shift pi over 54, lots of 577 to the power of 3 over 2 minus 1 to the power of 3 over 2 is just minus 1. So to 3SF, I make that 806 point stuff, but it's 0.2, so I make it 806 to 3 significant figures. That seems a bit weird. Let me just double check I've done this right. dy dx. Definitely dy by dx is 3 times 2, which is 6x squared. And if I square dy by dx, I'm 100% going to be getting 36x to the 4. If I let u equals to that, then du by dx, yeah, 4 36s are definitely 144. The 1 disappears. And I want a 2x cubed there. Yeah. Total surface area. Yeah, I guess so. Cool. Guess we're moving on. If I've made a mistake, just let me know. You might get a house point. You can show me where I went wrong. But I think that I've used it properly there. Anyway, if you want to have a go at this, pause the video. The curve C, shown in figure 1, has equation this. Use calculus to show the length of the curve is that. State the value of the constant k. Okay, so hopefully this should be a lot easier. So this is just going to be between 0 and ln A. My length, it's just going to be the integral of 1 plus dy by dx all squared dx. Okay, if y equals cosh of 3x, then I believe dy by dx is just going to be sine of 3x. I believe so. Cosh differentiates to sine. The 3 comes out, so it cancels with the third. Lovely jubbly. So this line integral just goes from ln A 0 integral of 1 plus sine squared of 3x dx. And then I believe 1 plus sine squared is cosh squared, so this just integral just becomes cosh of 3x dx. Cosh integrates to sine of 3x, and this is evaluated between ln of A and 0. And sine is e to the x minus e to the minus x all over 2. So I've actually got e to the ln A, which is A, minus e to the minus ln A, which is going to be 1 over A all over 2, minus, and then sine, oh, it's 3 lots of it, god damn. So this is actually 3A. No, it's not. Oh, you're a silly boy, Pope. You're a silly boy. 3 ln A is ln A cubed, so it's actually A cubed minus 1 over A cubed over 2. minus, and then sine of 0 is 0. So in actual fact, it's this. So I want it in the form of k lots of a cubed minus 1 over a cubed. So it looks like k is just 1/2, because I can write this as 1/2 of a cubed minus 1 over a cubed. Yeah, okay, so we've finished on an easy one. But yeah, guys, that's pretty much it. Yeah, so a lot of it is just being familiar that these equations exist, where they come from. I'd work through them if I were you, or you could just memorize them. They're going to be in the formula book, so don't worry about it. Reduction formula stuff is just so satisfying. So many step questions actually use the reduction formula. It's just so worth it. Even though it's not really tested, I just feel like so many questions you can bite through with such, celerity. Anyway, guys, hope you enjoyed it. Toodaloo.